For about 2,500 years, a strange kind of laboratory has existed that needs no equipment at all, just a quiet room and a question stated clearly enough to trap even the sharpest mind. Long before anyone could split an atom or scan a brain, thinkers were already running experiments they could never actually perform, freezing an arrow in mid-flight, filling a hotel that was already full, wiring a stranger's heart to yours while you slept. At the same time, something else has been quietly happening in your own head every single day. You flinch when a choice feels unfair before you can say why. You assume tomorrow will resemble today without ever proving it will. You trust that the person reading this sentence is really you. 50 of history's most famous thought experiments sit at the exact point where those two things meet, the deliberate traps built by philosophers and physicists, and the instincts you already carry into every one of them. Some will ask what you owe a stranger. Others will ask whether the floor beneath your certainty was ever as solid as it felt. One, involving a box, a cat, and a 50% chance, unsettled physics itself for the better part of a century. Settle in, there is no test here, and nowhere else you need to be for the next 2 hours, just 50 rooms to step into, one at a time, each one built to show you something true about the mind doing the stepping. A wooden ship sails out of harbour, and over the following 30 years every plank in its hull is replaced, one at a time, whenever the wood rots or splits. By the time the last worn plank comes out, not one piece of the original vessel remains, and yet sailors have called it the same ship, docked at the same berth, the entire time. The ancient historian Plutarch recorded the puzzle almost 2,000 years ago, describing an actual ship the Athenians kept in continuous repair as a monument, and asking a deceptively simple question: is the fully repaired ship still the same ship it was at the start? Most people's first instinct is yes, since the replacement happened gradually, one board at a time, with no single moment where the ship became a different object. But the philosopher Thomas Hobbes later sharpened the puzzle into something harder to dismiss. Suppose someone collected every discarded plank as it came out, board by board, and quietly reassembled them in their original positions into a second ship somewhere else. Now there are two ships. One has continuously occupied the harbour and carried the name the whole time. The other is built from every atom of the original material. Only one of them can be the real ship, if the word real is even doing honest work here. And there is no obvious rule for choosing between continuity of form and continuity of matter. The puzzle has outlived its wooden hull by centuries, because it was never really about ships. It resurfaces every time something replaces its own cells, its own habits of thought, one piece at a time, while everyone around it keeps calling it by the same name. The ship is still called by its name, and nobody has ever fully agreed on why that should be enough. 5 people are tied to a trolley track, unable to move, and a runaway trolley car is barreling toward them with no way to stop in time. You are standing beside a lever, pull it, and the trolley switches onto a side track, saving the 5, but killing one different person tied there instead. Nearly everyone asked this question says pull the lever. 5 lives outweigh 1, and the arithmetic feels almost too obvious to argue with. The philosopher Philip Foot introduced the scenario in 1967, not because she thought trolleys were an urgent moral problem, but because she wanted a clean way to isolate a distinction that shows up throughout ethics and law, the difference between actively killing someone and merely failing to save them, and the difference between causing harm as your goal versus causing it as an unavoidable side effect of doing good. Pulling the lever, in her framing, redirects an existing threat rather than creating a new one, which is part of why it feels different from other ways of trading one life for 5. Judith Jarvis Thomson later took the scenario further, building variation after variation, each one changing a single detail, whether the one person is a stranger or a relative, whether you touch the lever or a machine does it for you, whether the harm arrives as a side effect or as the entire point of the action. What she found is that the arithmetic alone never fully explains people's answers. Something else is doing quiet work underneath the numbers, something about intention, about touch, about what a person actually does with their own hands, and decades of psychology experiments since have mapped that hidden logic more precisely than philosophy alone ever could. Most people can tell you instantly what they would do at that lever, and almost none of them can fully explain why. A cat sits inside a sealed steel box, alongside a tiny amount of radioactive material, a Geiger counter, and a vial of poison gas rigged to break open the instant the counter detects a single radioactive decay. The odds of that decay happening within 1 hour are exactly 50%. According to the equations of quantum mechanics, until someone opens the box and looks, the cat is not simply alive or dead waiting to be discovered. It exists on paper, in a genuine mixture of both states at once. The physicist Erwin Schrödinger proposed the scenario in 1935, and he did not intend it as an endorsement of a living dead cat. He intended it as a complaint. Quantum theory, at the scale of individual atoms, allows a particle to exist in a blurred combination of two states simultaneously, a real and well-tested phenomenon called superposition. The trouble Schrödinger identified was that nothing in the mathematics stops that blur from scaling up. Wire the fate of something large and familiar, like a cat, directly to a single atomic event, and the same rules that govern the atom seem to demand that the cat itself becomes blurred too, an outcome that clashes badly with everything anyone actually observes about cats. Physicists still argue over how to resolve the tension. Some say the act of looking inside the box is itself the physical event that forces one outcome to become real. Others argue that both outcomes happen, splitting into separate, permanently disconnected branches of reality that never speak to each other again. No experiment has yet settled which explanation, if either, is correct, and the disagreement sits at the exact center of what physicists call the measurement problem. Open the box, and the cat was always simply alive or simply dead, and what quantum mechanics has never fully explained is what it was doing the moment before. Somewhere in a laboratory you have never seen, your brain could be resting in a jar of nutrient fluid, kept alive by machines, with every nerve ending wired into a supercomputer that feeds it a flawless simulation of exactly the life you believe yourself to be living at this very moment. Every sight, every sound, the weight of an object in your hand, all of it manufactured, indistinguishable from the real thing. The scenario descends from an older worry that has haunted philosophy since the 17th century, when René Descartes asked what would prove his senses were reporting on a real world rather than an elaborate deception. The philosopher Hilary Putnam reformulated the puzzle for a technological age in 1981, replacing the demon with a machine, and used it to ask a sharper question. What kind of evidence could you possibly point to that would rule this scenario out? Any proof you might offer, a memory, a photograph, the testimony of another person, would itself simply be part of the simulation if the scenario were true, which means the brain in the vat can never gather evidence against its own vat. Putnam went further than simply raising the worry. He argued that the scenario might actually be self-undermining, that a brain whose only contact with the world was a simulation could never even successfully refer to real vats or real brains in its own thoughts, since its words would only ever point to the simulated version. Whether or not that argument fully closes the door on the puzzle, it remains one of the cleanest illustrations of just how little separates ordinary confidence in the world from something that cannot, strictly speaking, be proven. The strange comfort, if there is one, is that a life fully convincing in every detail would look exactly like this one, whichever one it turns out to be. A man who does not understand a single word of Chinese sits alone in a locked room. Slips of paper covered in Chinese characters slide in through a slot. He has no idea what they mean, but he has an enormous rulebook, written entirely in English, that tells him exactly which characters to write back based on the shapes of the characters he received. He follows the rules perfectly, slides his response back out, and to anyone outside the room, the answers look like fluent, intelligent conversation in Chinese. The philosopher John Searle proposed this scenario in 1980 to challenge a claim that was gaining ground in the early days of artificial intelligence research, the idea that a computer running the right program could genuinely understand language, and even think simply by processing symbols correctly. Searle's point was that the man in the room is doing exactly what such a computer does, matching symbols to symbols according to formal rules, with zero comprehension of what any of it means. If the man does not understand Chinese, Searle argued, then a computer running the identical process on the identical rules cannot understand it either, no matter how convincing its answers appear from outside. Critics have pushed back for decades, arguing that while the man alone does not understand, perhaps the entire system, man plus rulebook plus room, understands in some collective sense the individual parts do not. Others argue that understanding was never really a well-defined target to begin with. The debate has never fully settled, but the thought experiment reshaped how philosophers and computer scientists talk about the difference between producing the right answer and actually knowing what the answer means. Somewhere behind every fluent response a machine gives you, that same locked room is still quietly running its rulebook. Mary has spent her entire life inside a room with no color in it at all, every surface painted in shades of black, white, and grey, and she has only ever watched the outside world through a black and white monitor. She is also, in this scenario, a brilliant scientist who has learned absolutely everything there is to know about the physics of color, every wavelength, every neural process that fires when a human eye detects red, every physical fact that exists on the subject, without exception. Then, one day, Mary walks out of the room and sees a ripe red tomato for the first time in her life. The philosopher Frank Jackson posed this scenario in 1982, and the question he wanted answered was simple: does Mary learn something new in that moment? Almost everyone's intuition says yes, that actually experiencing the color red for the first time gives her something her complete physical knowledge never could. But if she already knew every physical fact there was to know about color before walking out, and she still learns something new upon seeing it, then whatever she learns cannot be a physical fact. It seems to be something else entirely, something philosophers call qualia, the raw felt quality of an experience, and its existence would suggest that a complete physical description of the world, however thorough, might never fully capture what conscious experience actually is. Some philosophers have pushed back, arguing that what Mary gains is really just a new skill or a new way of representing facts she technically already had, not a genuinely new fact about the world. The disagreement remains one of the most argued questions in the philosophy of mind. Whatever Mary gained the moment she looked up, no equation she had memorized had fully prepared her for it. Imagine being handed the task of designing every rule that will govern a society, its taxes, its laws, its schools, its healthcare, but with one condition. You do not know, and will never know in advance, what position you yourself will occupy inside that society. You might be born wealthy or destitute, gifted or disabled, part of the majority or a persecuted minority, and the rules you design have to work for whichever one of those turns out to be you. The philosopher John Rawls called this imagined position the original position, and the temporary blindness to your own future circumstances, the veil of ignorance, laying it out in his 1971 book A Theory of Justice. His reasoning was that a person designing rules from behind such a veil would be forced to design them fairly, since they could not tilt the rules in their own favor without risking that the disadvantaged position they created might turn out to be their own. Someone who might end up poor would insist on a safety net. Someone who might end up part of a minority would insist on protections against the majority. Rawls argued that whatever principles a rational person would choose under those constraints deserved to be called genuinely just, since they were chosen without the self-interest that shapes almost every other political argument made from an already known position in the world. Critics have questioned whether people behind the veil would really choose the specific principles Rawls predicted, or whether truly impartial reasoning is even possible for a mind that knows it will eventually step back out from behind the veil. But the device itself has become one of the most widely used tools in modern political philosophy. Very few of us ever design a society, and yet all of us, at some point, quietly decide what fairness would require if the next life drawn from the veil were our own. A shepherd named Overgrazes discovers a ring buried in a chasm and finds that turning its collet toward his palm makes him completely invisible. Once he understands what he holds, he uses the ring to enter the royal palace unseen, seduce the queen, murder the king with her help, and take the throne for himself, all without a single witness, all without a single consequence. The story appears in Plato's Republic, told by the character Glaucon, who uses it to pose an uncomfortable challenge to Socrates. Glaucon argues that people are only ever just because they fear getting caught, and that if any person, however honest, were given a ring that guaranteed total impunity, they would behave exactly as JYGs did. Take away every consequence, Glaucon says, and justice reveals itself as nothing more than a performance kept up for an audience, not something anyone actually values for its own sake. Socrates spends much of the rest of the Republic trying to answer that challenge, arguing that a just soul is internally ordered and at peace with itself in a way an unjust soul, however successful and unpunished, can never be, so that even a perfectly hidden crime damages the person who commits it from the inside. Whether that answer actually satisfies Glaucon's challenge has been argued over for well over 2,000 years, and the scenario has been reused countless times since, in stories about invisibility, anonymity, and unwatched power, always circling back to the same uncomfortable question about what a person actually is, underneath the eyes that happen to be watching them. The ring has never existed, but the question of who you would be while wearing it still does. Deep inside a cave, a group of prisoners has been chained in place since childhood, forced to face a blank wall, unable to turn their heads. Behind them, hidden from their view, a fire burns, and people pass in front of it carrying objects. Casting shadows onto the wall, the prisoners are forced to watch. The prisoners have never seen anything else. To them, the shadows are not a representation of reality. The shadows are reality, complete and total. Plato describes this scene in the Republic to dramatize the philosopher's task and to explain why that task is so often unwelcome. One prisoner is freed, forced to turn around, and sees the fire for the first time, painfully bright after a lifetime in near darkness. Dragged further out of the cave entirely, he sees the sun itself, and slowly comes to understand that everything he once took for the whole of reality was only ever a flickering imitation of something larger and more real. Plato's question is what happens next. Does the freed prisoner return to the cave to tell the others what he has seen? And if he does, will they believe him, or will his strange talk of a world of sunlight, so different from the shadows they know, mark him as someone who has lost his mind? Plato suggests they will not welcome him. They may even try to kill him rather than climb out themselves, since the climb is difficult, and the shadows, whatever else they are at least familiar. The allegory has outlived every specific belief Plato held, because the shape of it keeps recurring. Any comfortable, limited view of the world resists the person who has seen past it, however true that person's report might be. Everyone who has ever tried to explain something genuinely new to someone still facing the wall knows exactly how that sensation tends to go. You wake up one morning in a hospital bed, and a doctor explains what has happened. During the night, the Society of Music Lovers kidnapped you and surgically connected your circulatory system to that of a world-famous violinist whose kidneys have failed. For the next 9 months, his survival depends entirely on staying plugged into your body. Unplug him early, even for a moment, and he dies. Stay connected the full 9 months, and he recovers completely and can be safely disconnected. The philosopher Judith Jarvis Thomson introduced this scenario in a 1971 essay, and she built it specifically to test an argument she thought was too quick: the claim that if a fetus has a right to life, that right alone settles every question about abortion, since ending a pregnancy would then simply be killing something with a right not to be killed. Thomson agreed, for the sake of argument, that the violinist has a right to life. Her question was whether that right, on its own, obligates you to remain physically connected to him for 9 months against your will. Most people who hear the scenario say no, that even granting the violinist a right to life, you are not thereby required to keep your own body attached to his for so long, however admirable it would be if you chose to. Thomson used the gap between those two answers to argue that a right to life is not automatically a right to use someone else's body without their ongoing consent, a distinction she believed had been quietly skipped over in simpler versions of the debate. The scenario remains one of the most cited and most contested thought experiments in the philosophy of bodily autonomy, precisely because almost everyone has a strong intuition about it, and those intuitions do not always point where the surrounding argument expects. Whatever you decide the violinist is owed, the harder question was never really about him at all. You are standing on a footbridge that crosses directly over the trolley track, high enough above it that jumping yourself would do nothing but add a second casualty. Beside you stands a large stranger, easily heavy enough to stop the runaway trolley if he landed on the track in its path. The only way to save the 5 people tied further down the line is to push him off the bridge yourself, with your own hands. The numbers here are identical to the classic trolley problem, 1 life against 5, but where most people asked the original version say pull the lever without much hesitation, the same people, faced with this version, overwhelmingly refuse to push. Philosophers have spent decades trying to explain the gap between those two answers, since a purely mathematical view of the situation treats them as exactly the same trade. One influential explanation points to the difference between using someone as a means and merely redirecting an existing danger. In the lever version, the trolley's threat is redirected, and the one death is an unfortunate side effect of saving the 5. In the footbridge version, the stranger's body is the actual mechanism that stops the trolley. His death is not a side effect at all, it is the plan. Another explanation focuses on the physical directness of pushing someone with your own hands, a kind of harm that registers differently in the mind than harm delivered at a distance through a lever or a switch. Researchers studying moral psychology have used brain scans to show that the footbridge version activates emotional circuitry that the lever version barely touches, suggesting the two scenarios are not processed by the same part of the mind at all, however similar the underlying arithmetic looks on paper. Ask someone to do the math, and the two versions look the same, but ask someone to actually do it, and almost nobody treats them that way. A skilled surgeon has 5 patients on the ward, each dying of organ failure, each needing a different organ, a heart, a liver, 2 kidneys, a pair of lungs, and none of them likely to survive the week without a transplant. A healthy young man arrives for a routine physical, and a blood test reveals that his organs are a perfect match for all 5. He has no family expecting him, and no one would ever trace his disappearance back to the hospital. The scenario is a deliberately harder cousin of the trolley problem, built specifically to pressure test a simple form of utilitarian reasoning, the idea that the right action is always whichever one produces the greatest total well-being, counted up like a ledger. On a pure head count, killing the one healthy visitor to save 5 dying patients looks like an improvement, 5 lives gained against 1 lost, the same ratio that makes pulling the trolley lever feel obviously correct to most people. And yet almost no one, philosopher or otherwise, thinks the surgeon should do it. Something about actively killing an unsuspecting, uninvolved person, someone who was never already in danger, someone who walked in trusting the hospital to help him, feels categorically different from redirecting a threat that already existed. Philosophers have used the gap between this case and the trolley problem to argue that people's moral intuitions are tracking something more specific than a simple head count, something closer to a right against being used as a resource for someone else's benefit without consent, a right that holds even when violating it would produce a better outcome by the numbers. The math never stopped adding up in the surgeon's favor, but it never once told anyone whose organs those 5 patients were actually entitled to take. Suppose for a moment that an immensely powerful and immensely deceitful demon exists, and that this demon has directed the entirety of its cunning toward one single purpose, to deceive you completely, arranging every sight, every sound, every memory you possess, so that nothing you have ever perceived can be trusted as genuine. The philosopher René Descartes proposed this scenario in his 1641 work Meditations on First Philosophy, not because he believed such a demon actually existed, but because he wanted to find the most extreme form of doubt imaginable, in order to discover whether anything at all could survive it. He doubted his senses, since senses can deceive. He doubted mathematics, since even a simple calculation could, in principle, be manipulated by a sufficiently powerful deceiver. He doubted the existence of his own body, since a demon capable of falsifying every sensation could just as easily falsify the sensation of having a body at all. What Descartes found at the very bottom of this process was one thing the demon could never successfully fake, the fact that doubting itself was happening. A demon could deceive him about the content of his thoughts, but it could not make it false that thinking was occurring, because the very act of being deceived requires a thinker there to be deceived. From that single, undoubtable point, captured in the phrase "I think, therefore I am," Descartes tried to rebuild a foundation for everything else he claimed to know, arguing his way back out toward the reliability of reason, the existence of a benevolent God, and eventually the trustworthiness of the external world his senses reported on. Later philosophers found that path back out far less convincing than the doubt that started it, and the demon has proven remarkably difficult to fully banish ever since, resurfacing centuries later, wearing the shape of a machine and a vat of nutrients instead of a monster. The costume the doubt wears keeps changing, but the question underneath it never quite goes away. Somewhere, in principle if not in practice, there could exist a being physically identical to you down to the last atom, a being with a brain that fires in exactly the same patterns yours does, who winces when he stubs his toe, laughs convincingly at a joke, tells you in detail how sad he is after a loss, and yet on the inside there is nothing there at all, no felt experience, no inner light, just the outward behavior of a conscious being running with nobody home. Thought experiments like this one appear throughout the philosophy of mind, but the version that shaped modern debate was popularized by the philosopher David Chalmers, who used it to sharp what he called the hard problem of consciousness. The easy problems of consciousness, Chalmers argued, are things like explaining how the brain processes information, integrates sensory input, or produces behavior, all of which science is steadily making progress on. The hard problem is different. Even a complete map of every neuron firing in your brain does not, by itself, explain why any of it is accompanied by subjective experience at all, why there is something it feels like to see red or taste coffee, rather than all that processing happening in the dark, unaccompanied by any inner life whatsoever. If a zombie exactly like you, minus the inner life, is even conceivable without logical contradiction, Chalmers argued, then consciousness cannot simply be identical to physical brain activity, since two physically identical systems could then differ in whether anyone is home. Critics reply that if such a zombie is truly physically identical down to every atom, then imagining it lacking consciousness might be a failure of imagination rather than a real possibility, the same way it once seemed conceivable that water could turn out not to be made of hydrogen and oxygen. Nobody has ever met a zombie of this kind, and nobody has ever fully proven that one could not quietly exist beside them. Neuroscientists have built a machine, in this scenario, capable of stimulating your brain to produce any experience you could possibly want, indistinguishable in every respect from the real thing, for the rest of your natural life. Floating in a tank, connected by electrodes, you could live out a lifetime exactly as rich and satisfying as you designed it, achieving every goal, meeting every person, feeling every joy you could imagine, and once you were plugged in, you would have no memory of ever having chosen the machine at all. The philosopher Nozick proposed this scenario in his 1974 book Anarchy, State and Utopia, aimed squarely at a simple and common view of the good life, the idea that pleasurable experience is the only thing that ultimately matters, and that a life should be judged purely by how it feels from the inside. If that view were correct, Nozick reasoned, everyone confronted with the machine should want to plug in immediately, since it offers a guaranteed maximum of exactly the kind of experience the theory says is all that counts. Yet, when Nozick asked people the question directly, the overwhelming majority said no, they would not plug in, even knowing the simulated life would feel every bit as good as a real one. Nozick took that widespread refusal as evidence that people care about more than how their life feels from the inside. They care about actually doing things, not merely having the experience of having done them, about being connected to real people rather than simulated ones, and about being a particular kind of person in the world, rather than a body floating in a tank generating convincing sensations. The thought experiment has since become one of the standard arguments against treating pleasure as the entire measure of a life well lived. Given the choice, almost everyone quietly chooses the harder, realer version of their own life over the guaranteed one. Picture a hungry donkey standing precisely halfway between two piles of hay, identical in size, identical in freshness, identical in every measurable way, with the donkey equally hungry for either one, lacking any reason whatsoever to prefer one pile over the other. The donkey, according to the puzzle, simply stands frozen between them, and starves to death exactly at the midpoint, unable to break the perfect tie. The scenario has long been attached to the name of the medieval French philosopher Zahen-Byor-e-Dahen, though, somewhat fittingly for a puzzle about paralysis, no surviving text of his actually contains the donkey in this exact form. What Buridan did write about was the idea that a rational will, faced with two options judged to be exactly equally good, has no basis on which to choose, since choice requires some reason to favor one option, and by definition, in this scenario, no such reason exists. Later thinkers turned that abstract observation into the vivid image of the starving donkey to test whether pure, unemotional rationality could ever actually produce action in a genuine tie, or whether some other factor entirely, chance whim, or a small emotional nudge with no rational justification behind it, has to break every tie a purely logical mind could never break on its own. Some philosophers have argued the puzzle reveals a real gap in classical theories of rational choice, while others point out that real agents almost never face a truly perfect tie, and that the donkey's fatal paralysis says more about the artificial cleanliness of the thought experiment than about how choice actually works in the world. No real donkey has ever starved this way, and no philosopher has ever fully agreed on what, exactly, would finally make it move. Achilles, the fastest runner in the Greek world, agrees to race a tortoise, and to make the contest fair, he gives the slow tortoise a head start. The race begins, and Achilles quickly closes the distance to where the tortoise started, but by the time he arrives there, the tortoise, however slowly, has already moved a little further ahead. Achilles closes that new gap too, only to find the tortoise has again advanced, if only by a fraction. This pattern, in principle, repeats itself without end. The philosopher Zeno of Ilia proposed this puzzle around the 5th century BC, and it survives today only because Aristotle quoted and argued against it in his own writings centuries later. Zeno's actual target was not foot races at all. He was defending the philosophical position of his teacher Parmenides, who argued that change and motion were, at the deepest level, illusions, and Zeno built a series of paradoxes designed to show that the ordinary belief in motion led to logical contradictions when examined closely enough. In this version, dividing the race into an infinite sequence of ever smaller catch-up moments seems, on the page, to prevent Achilles from ever fully passing the tortoise, even though everyone watching the actual race would see him do exactly that within seconds. The eventual resolution came only with the mathematics of infinite series, developed over 2,000 years later, which showed that an infinite number of intervals can still sum to a finite total distance covered in a finite amount of time, a genuinely counterintuitive fact about infinity that Zeno's contemporaries had no mathematical language to express. Anyone can watch the fast runner pass the slow one in an instant, but writing down exactly why the argument against it fails took humanity a great deal longer. Picture an arrow in flight, and picture time itself as a sequence of instants, each one a razor-thin slice with no duration at all. At any single one of those instants, the arrow occupies one specific position in space, no more and no less, exactly the way it would if it were simply sitting motionless on a table. Zeno of Ilia, the same philosopher behind the puzzle of Achilles and the tortoise, argued that if the arrow is indistinguishable from a stationary object at every individual instant of its flight, and if the entire flight is nothing more than a long sequence of such instants strung together, then there is no instant anywhere in that sequence at which the arrow can genuinely be said to be moving. And if it is never moving at any instant, Zeno reasoned, then in what sense is it moving at all across the whole flight? The paradox exposes a real tension between two different ways of understanding time, as a smooth, continuous flow, or as a sequence of discrete, motionless snapshots stitched together, and calculus would eventually be developed, centuries later, specifically to handle the mathematics of change occurring across intervals, built from instants with zero duration. Modern physics has its own unresolved echoes of this same tension, in ongoing debates about whether time is fundamentally continuous or built from indivisible smallest units, debates that trace a surprisingly direct line back to Zeno's frozen arrow. Photographers who freeze a moving object with a fast shutter capture something remarkably similar to that frozen instant, a single motionless slice pulled from continuous motion, though no one mistakes the photograph for proof that the object was never moving at all. The arrow lands exactly where it was always going to land, and no one has ever fully explained, to everyone's satisfaction, the instant it started moving to get there. Before you can walk from one side of a room to the other, you must first cross half that distance. But before you can cross that half, you must first cross half of it, a quarter of the total distance, and before that quarter, an eighth, and before that eighth, a 16th, an infinite sequence of ever smaller halfway points stretching backward from wherever you currently stand. Zeno of Ilia used this structure to argue that completing any journey at all requires finishing an infinite number of separate steps, and that finishing infinitely many steps in a finite stretch of time seemed, to him and to his contemporaries, to be a plain logical impossibility. If motion truly required this endless subdivision, no journey, however short, could ever actually begin, since it would first require completing the second half of an already infinite regress. Yet people cross rooms constantly, without any apparent difficulty, which is precisely the tension Zeno wanted to expose. A place where careful logical reasoning seemed to collide head-on with the most basic evidence of the senses. The eventual mathematical answer came through the concept of a convergent infinite series, the discovery that an infinite number of terms, each one smaller than the last, can still add up to a perfectly ordinary finite total, the way 1/2 plus 1/4 plus 1/8 plus every fraction after it sums cleanly to exactly one whole. Zeno's contemporaries had no such tool available to them, which is part of why the paradox held its grip on Greek philosophy for as long as it did, unresolved by anything sturdier than the observation that people obviously do cross rooms. Nothing about walking across a room has ever actually stopped working, no matter how many times the argument against it gets rebuilt. Consider a single sentence, written on its own, making one plain claim about itself. This sentence is false. Read it carefully and try to decide whether it is true or false, and the sentence will not let you land anywhere and stay there. If it is true, then it is accurately reporting itself to be false, which means it must actually be false. But if it is false, then its own claim that it is false turns out to have been true after all. The paradox is ancient, traced back to the Greek logician Eubulides of Miletus in the 4th century BC, and it has resisted a fully agreed resolution for well over 2,000 years since. Some logicians have argued that the sentence simply fails to express a coherent proposition at all, so that asking whether it is true or false is a bit like asking whether the color blue weighs more than Tuesday, a question with no real content to answer. Others have proposed elaborate systems that assign sentences a third value beyond true and false, or that forbid sentences from directly referring to their own truth in the first place. The stakes turned out to be far higher than a piece of clever wordplay. In the 20th century, the mathematician Kurt Gödel adapted the same self-referential structure, a statement effectively claiming its own unprovability rather than its own falsehood, to demonstrate that any sufficiently powerful mathematical system must contain true statements that the system itself can never prove, a result that reshaped the foundations of mathematics and logic for good. A single short sentence, doing nothing more than talking about itself, turned out to be sturdy enough to still be standing between mathematics and certainty a century later. In a certain village, one barber has made a strict rule for himself. He shaves every man in the village who does not shave himself, and he shaves no one who does shave himself. It sounds like a perfectly ordinary, sensible rule for a small-town barber to live by, until you ask one simple question about the barber himself. Does the barber shave himself? If he does, then according to his own rule, he only shaves men who do not shave themselves, which means he must not shave himself, a direct contradiction. If he does not shave himself, then according to that same rule, he is exactly the kind of man he shaves, which means he must shave himself, again a direct contradiction. There is no consistent answer. The rule, applied honestly to its own creator, simply breaks. The philosopher Bertrand Russell popularized this puzzle in the early 20th century as an accessible, everyday version of a much deeper problem he had discovered lurking inside the foundations of mathematics itself, a problem involving sets that do or do not contain themselves as members. Mathematicians at the time had been building an entire framework, naive set theory, on the assumption that any coherent description could define a valid set, until Russell showed that some descriptions, applied to themselves, generate exactly this kind of unavoidable contradiction. The Barber puzzle made the abstract mathematical problem intuitive to anyone who had ever walked into a small shop for a haircut, even as the underlying discovery forced professional mathematicians to rebuild their entire field from more careful foundations. Somewhere in the tidy logic of a village with one barber, an entire branch of mathematics quietly ran out of road. Mathematics, before the 20th century, generally assumed that any clearly stated property could define a set, the collection of everything that has that property, the set of all red apples, the set of all even numbers. It seemed like a completely safe assumption. Then consider one particular set, the set of every set that does not contain itself as one of its own members. Ask whether that set contains itself, and the same contradiction that trips up the village barber appears in purer, more abstract form. If the set does contain itself, then it fails to meet its own defining condition, not containing itself, so it should not be a member after all. If it does not contain itself, then it satisfies its own defining condition perfectly, which means it should be a member, so it does contain itself. The philosopher and mathematician Bertrand Russell discovered this contradiction in 1901, while examining the foundational work of the German logician Gottlob Frege, who had just spent years building an entire system of mathematics on the naive assumption that any coherent description defines a legitimate set. Russell's letter informing Frege of the paradox arrived just as Frege's major work was going to print, and Frege was forced to add a hurried postscript acknowledging that the foundation of his life work had just been shown to be inconsistent. The discovery did not destroy mathematics. It forced mathematicians to rebuild set theory on more careful, restricted foundations, distinguishing which descriptions are actually allowed to define a set and which ones, like Russell's own paradoxical example, are not, a repair that still underlies the mathematics taught in universities today. An entire field once had to stop, mid-construction, and rebuild its own foundation from underneath a single sentence. Could a being with unlimited power create a stone so heavy that even that same unlimited power could not lift it? The question sounds almost childish at first, the kind of trick posed by a clever schoolchild, but it traps the concept of omnipotence in a genuine bind, no matter which way you answer it. If the all-powerful being cannot create such a stone, then there is at least one thing it cannot do, and its power appears to have a limit after all. If it can create the stone, but then finds itself unable to lift it, its power has a limit anyway, just a different one. Either answer seems to undercut the very idea of unlimited power the question set out to test. Medieval philosophers took the puzzle seriously rather than dismissing it as wordplay, and several distinct responses emerged over the centuries. One approach argues that genuine omnipotence only requires the ability to do anything that is logically possible, and that a stone simultaneously liftable and unliftable by the same unlimited power is not a coherent task at all, no different from asking whether an all-powerful being could create a square circle, a request that fails before power even enters the picture. Another response distinguishes between a being's power in the present moment and its power considered across all possible states, arguing the paradox conflates the two. The disagreement has never fully settled, in part because it hinges on a deeper, unresolved question: whether logical impossibility genuinely limits omnipotence, or whether omnipotence was never meant to cover the logically impossible in the first place. No stone like that has ever needed lifting, and the argument over what would happen if one did has outlasted every philosopher who first raised it. Is a pious action pious because the gods love it, or do the gods love it because it is already pious, independent of their approval? The question sounds abstract, almost a matter of wordplay, until you notice that it applies to every religious or authoritative claim about morality ever made, in any tradition at any point in history. Plato poses the question in his dialogue Euthyphro, staged as a conversation between Socrates and a young man named Euthyphro, who is confidently prosecuting his own father for a religious crime, certain he understands piety well enough to judge it. Socrates presses him on where that certainty actually comes from, and the dilemma that emerges has never stopped mattering. If something is good purely because a divine authority commands it, then goodness looks arbitrary, changeable on a whim, since the same authority could, in principle, have commanded the opposite and made cruelty count as virtue instead. But if the divine authority commands something because it is already, independently, good, then goodness exists on its own terms, and the authority is simply recognizing it rather than creating it, which means morality does not actually depend on that authority after all. Neither horn of the dilemma leaves divine command as a simple, self-sufficient foundation for ethics. Philosophers since Plato have proposed various ways to soften the bind, distinguishing between a being's nature and its commands, for instance, but the basic tension Euthyphro exposed, between authority and independent goodness, resurfaces every time any powerful institution claims the sole right to define what is right. 25 centuries later, the question a young man asked his father's accuser has outlived every specific god it was ever asked about. You cannot prove, through pure reason alone, whether God exists. The mathematician and philosopher Blaise Pascal accepted that limitation completely, and then made an argument that reason alone should still push you toward belief, treating the question less like a matter of evidence and more like a wager you are forced to place with your entire life, whether you want to or not. Pascal laid out the four possible outcomes plainly. Believe and God exists, and the reward is an infinite, eternal gain. Believe, and God does not exist, and you have lost comparatively little, some worldly pleasures foregone. Disbelieve, and God exists, and the loss is infinite, an eternity of consequence. Disbelieve, and God does not exist, and you gain only a modest, finite advantage in this one life. Laid out as expected value, Pascal argued, only one choice makes rational sense, since any finite cost or gain is overwhelmed by even a small chance of an infinite one. The wager appeared in the Pensies, a collection of Pascal's notes published after his death around 1670, and it remains a foundational case study in decision theory as much as in religion, precisely because its logical structure, weighing finite costs against a possible infinite payoff, keeps resurfacing in entirely secular arguments about existential risk, about long-term consequences, about any decision where one branch of the outcome tree dwarfs all the others in scale. Critics have raised sharp objections, questioning which God exactly the wager should point toward, and whether belief adopted purely for strategic reasons could ever count as genuine faith at all. Whatever you conclude about the wager's soundness, Pascal built it convinced that indifference itself was already a bet, whether anyone admitted to placing it or not. If a God exists who holds unlimited power, unlimited knowledge, and perfect goodness all at once, a question follows that has occupied theologians and philosophers for well over 2,000 years. Why does suffering exist in the world at all? An all-powerful being could presumably eliminate suffering outright. An all-knowing being would certainly be aware of every instance of it. A perfectly good being would, it seems, want to prevent it wherever possible. Hold all three attributes together: unlimited power, unlimited knowledge, perfect goodness, and the continued existence of suffering starts to look like it requires giving up at least one of them. The riddle is frequently attributed to the ancient philosopher Epicurus, though historians of philosophy note that the precise wording usually quoted cannot be reliably traced back to any surviving text of his, and its true origin remains genuinely uncertain, regardless of the name usually attached to it. What has never been uncertain is how seriously the problem has been taken across religious traditions ever since. Responses have varied widely. Some argue that suffering is the necessary cost of genuine free will, since a world where wrongdoing was made impossible would not be a world of free moral agents at all. Others argue that suffering serves a larger purpose beyond human comprehension, one that a limited human perspective simply cannot evaluate from the inside. Neither response has ever fully satisfied every critic, and the tension between the three divine attributes and the plain fact of suffering remains one of the most enduring and most seriously debated problems in the philosophy of religion. No single answer to the riddle has ever managed to end the conversation it started. Imagine walking across an empty heath and coming across a stone lying on the ground. You would likely assume without much thought that the stone had simply always been there, shaped by nothing more than wind and time. But imagine, instead, finding a watch lying in the grass, its gears meshing precisely, its springs coiled with obvious purpose, every part clearly arranged to keep time. You would not conclude that the watch had simply always existed in that form. You would conclude, immediately and reasonably, that it must have had a maker. The clergyman William Paley developed this comparison at length in his 1802 book Natural Theology, arguing that the intricate, purposeful design visible throughout the living world, the eye, the wing, the exact interlocking mechanisms of a living body, calls for a maker in exactly the same way the watch does, only on a far grander scale. If a comparatively simple machine like a watch demands a watchmaker, Paley reasoned, then the staggering complexity of a living organism demands a designer of even greater intelligence and precision. The argument became one of the most widely read and widely taught defenses of intelligent design for much of the 19th century. Charles Darwin encountered Paley's argument directly as a student at Cambridge and admired its clarity, even as he later devoted much of his own career to developing a rival explanation, natural selection, for how the appearance of purposeful design could arise gradually, without any designer at all, purely improve survival across countless generations. The watch was never in question. What its existence was supposed to prove is still being argued over, 2 centuries and one theory of evolution later. Every single day of your life, without exception, the sun has risen. You have never once seen it fail to do so, and neither has anyone else in recorded history. It would seem, on the strength of that evidence, like about as safe a bet as exists, that the sun will rise again tomorrow morning. The philosopher David Hume pointed out, in his 1748 Enquiry Concerning Human Understanding, that this confidence rests on an assumption that cannot actually be proven, the assumption that the future will resemble the past. Every argument you might offer for why the sun will keep rising, that it always has before, that the laws of physics are stable, that nature does not change its habits, ultimately relies on the same unproven premise, that patterns observed so far will continue to hold going forward. You cannot justify that premise by pointing to more past observations, since that simply repeats the same assumption rather than proving it. Hume was not suggesting the sun might actually fail to rise. He was pointing out something more unsettling, that our entire practice of learning from experience, the basis of nearly every science and every ordinary judgment about the world, rests on a habit of expecting repetition rather than on anything logic alone can fully guarantee. Attempts to solve what came to be called the problem of induction have continued for nearly 3 centuries since, and no solution has commanded anything close to universal agreement among philosophers, even as scientists, quite reasonably, keep right on relying on the pattern anyway. Nothing about tomorrow's sunrise is actually in doubt. What remains unsettled is only the reasoning that lets anyone say so with total certainty. Consider the ordinary, unremarkable claim that all ravens are black. To gather evidence for it, the obvious approach is to go out and look at ravens, and every black raven you find does indeed support the claim a little further. But formal logic points out something stranger. The statement, all ravens are black, is logically identical to a second statement. All things that are not black are not ravens, and if the two statements are truly equivalent, then anything that confirms one must also confirm the other. That means a green apple, an object with nothing whatsoever to do with birds, technically counts as a non-black thing that is also a non-raven, and therefore, by strict logic, counts as a small piece of confirming evidence for the claim that all ravens are black. The philosopher Carl Gustav Hempel identified this puzzle in the 1940s, and it has become known as the Raven paradox, a case where the formal rules of logical confirmation and ordinary human intuition about what counts as real evidence pull sharply apart. Few people, looking at an apple, would say they had just learned something new about ravens, and yet the logic connecting the two claims is airtight. Philosophers have proposed various responses, some arguing the apple really does provide an infinitesimally small amount of genuine evidence, just far too small to notice, others arguing that the background context in which we ask questions, how many ravens versus how many non-black objects exist in the world, quietly does most of the real work that intuition is actually tracking. An apple has never once told anyone anything they felt was worth knowing about a raven, and yet logic has never quite let it off the hook. Every emerald that has ever been examined, without a single exception, has been green. On the strength of that evidence, it seems entirely reasonable to predict that the next emerald ever discovered will also be green. But the philosopher Nelson Goodman pointed out, in his 1955 book Fact, Fiction and Forecast, that the exact same evidence supports a second, stranger prediction equally well. Define a new property, GRU, as applying to anything examined before some future date, say January 1st of next year, that is green, or anything examined after that date that is blue. Every emerald examined so far has in fact been GRU as well as green, since every single observation happened before the cutoff date. The evidence collected up to now cannot distinguish between the hypothesis that all emeralds are green and the hypothesis that all emeralds are GRU, because both predictions agree perfectly on every observation made so far, and only diverge on emeralds examined after the future date, which by definition no one has checked yet. Goodman built this puzzle to sharpen David H. Hume's older problem of induction into something even more precise, that even a perfect track record of past observations cannot, by pure logic alone, tell you which of two equally well-supported predictions about the future is the correct one to trust. Something beyond raw observation, some deeper preference for properties like green over invented ones like GRU, has to be doing quiet work in the background of every prediction anyone ever makes from past evidence, and philosophers still disagree about exactly what that something is, or how to justify it without simply assuming the answer in advance. Every emerald found tomorrow will very likely still be green, though nothing in the evidence collected up to today can fully explain why that should be the safer. A heap of sand containing 10,000 individual grains is unmistakably, obviously a heap by anyone's judgment. Remove a single grain, and it is still, just as obviously, a heap. Removing one grain from a heap has never turned it into a non-heap, not once, not ever, and that premise seems completely safe to accept. But repeat the process, one grain at a time, 10,000 times, and you eventually arrive at a single remaining grain of sand, sitting alone, which is just as obviously not a heap by anyone's judgment. Somewhere between 10,000 grains and one grain, the heap stopped being a heap, and yet every single step along the way seemed to preserve heapness perfectly, according to the very premise that started the whole process. The paradox is traced to the ancient logician Eubulides, working in the 4th century BC, the same figure credited with the liar's paradox, and it exposes something genuinely strange about an enormous number of ordinary words. Heap has no precise cutoff. Neither does bald, or tall, or rich, or young, words that come in continuous shades rather than sharp, countable boundaries, and yet people use these words confidently every single day without any trouble at all. Logicians have proposed several distinct responses. Some argue that a precise cutoff does exist somewhere, just permanently unknowable to us. Others build entirely new systems of logic that allow statements to be partly true rather than strictly true or false, assigning something like 70% heapness to a pile of 5,000 grains. No single approach has one universal agreement, and the paradox remains a central case study anywhere vague language meets rigorous, exact reasoning. Nobody can point to the exact grain where the heap disappeared, and yet everybody, somehow, still knows a heap when they see one. A sealed envelope is placed in your hands, containing an unknown amount of money, and you are told that a second sealed envelope sits nearby, containing either exactly twice as much money as yours, or exactly half as much, with an equal chance of either. Before you decide whether to keep your envelope or switch, someone runs through a simple calculation with you. Call the amount in your envelope a certain sum. If you switch, there is a 50% chance the other envelope holds double that sum, and a 50% chance it holds half that sum. Average those two outcomes together, and the expected value of switching comes out higher than the sum you are currently holding, no matter what that sum actually is. So it seems you should always switch. Here is the trouble. The exact same calculation, run from the perspective of the other envelope, gives the identical result, that switching to your envelope is the better move. Both envelopes cannot simultaneously be the mathematically superior choice to hold, since switching back and forth forever would be absurd, and yet the reasoning behind each individual switch looks completely sound on its own. Something in the calculation is quietly going wrong, but locating the exact error has occupied mathematicians and philosophers for decades, since the assumptions baked into the setup about how the unknown starting sum was actually chosen, and what a 50% chance really means when no concrete numbers have been specified yet, turn out to matter far more than the tidy arithmetic on the surface suggests. Two identical envelopes, and a piece of reasoning convincing enough to make you want to switch forever in either direction without ever actually opening either one. A casino offers a simple game. A fair coin is flipped repeatedly until it lands tails, and the payout doubles with every consecutive heads that comes before that first tails. Land tails on the very first flip, and you win $1. Flip heads once before the first tails, and you win $2. Flip heads 10 times running before the first tails, and the payout has already grown past $1,000, and it keeps doubling for as long as heads keeps coming up. Calculate the mathematically expected winnings of this game, averaged across every possible outcome, and the total comes out infinite, since the tiny but non-zero chance of an enormously long streak of heads contributes an unboundedly large amount to the average. By the standard logic of expected value, a rational gambler should be willing to pay almost any entry fee to play a game with infinite expected winnings. Yet the mathematician Nekhar Bernoulli, who posed the puzzle in 1713, observed that almost nobody would actually pay more than a very modest sum, somewhere in the range of a few dollars, to play. His cousin, Daniel Bernoulli, proposed an answer in 1738 that reshaped economics for centuries afterward, suggesting that people do not value money in a straight additive way at all. Each additional dollar, Daniel Bernoulli argued, provides slightly less added satisfaction than the dollar before it, so that an astronomically large but astronomically unlikely payout is worth far less to an actual human being than its raw expected value on paper would suggest. The math says the game should be worth an unlimited sum to play, and almost no one who has ever heard the terms has agreed to bet accordingly. You are shown 2 jars, each containing 100 balls, some red and some black. In the first jar, you are told plainly that exactly 50 balls are red and 50 are black. In the second jar, you are told only that the balls are some unknown mixture of red and black, with no further information given at all. You are then offered an identical bet on each jar, a modest prize if you draw a red ball. Most people offered this choice prefer to bet on the first jar, the one with known, fixed odds, even though the true odds in the second jar could, for all anyone actually knows, be exactly as favorable or even more favorable than the first. The economist Daniel Ellsberg documented this pattern carefully in 1961 and gave it a name, ambiguity aversion, a preference for known risk over genuine, unquantified uncertainty that standard mathematical decision theory struggled to explain. Under the classical model of rational choice, a person should simply calculate expected outcomes using whatever probability estimate seems most reasonable for the unknown jar. And if that estimate comes out equal to 50%, the 2 jars should feel equally attractive to bet on. Ellsberg's experiments showed that people do not behave this way at all. They treat the mere absence of known odds as a cost in itself, separate from the odds actually being unfavorable, suggesting that human decision-making tracks not just probability, but confidence in the probability estimate, a distinction the tidy mathematics of expected value had never made room for. Handed a bet with unknown odds, most people flinch first, and only calculate afterward. You are a contestant on a game show facing 3 closed doors. Behind one is a car. Behind the other 2 are goats. You pick a door, say door number 1, and before it is opened, the host, who knows exactly what is behind every door, opens a different door, say door number 3, revealing a goat. You are then offered a choice: stick with your original door, or switch to the one remaining unopened door. Most people's instinct says it no longer matters, that with 2 doors left, the odds are now an even 50-50, so switching is pointless. That instinct is wrong, and proving it wrong caused one of the most famous controversies in recreational mathematics. The columnist Mer-Arlin Voss Sa VH&T answered a reader's letter about the puzzle in 1990, correctly stating that switching doors doubles your odds of winning, from 1 in 3 up to 2 in 3. The response was fierce. Thousands of readers wrote in to disagree, including a substantial number of mathematicians and statisticians with advanced degrees, many of them condescendingly certain she had made an elementary error. She had not. The key detail everyone missed is that the host's action is not random. He always opens a door he knows conceals a goat, which means his choice carries information, quietly folding the 1/3 probability originally sitting on your unchosen doors into the single door he leaves closed. Repeated computer simulations and rigorous mathematical proofs eventually settled the matter beyond dispute, exactly as Voss Savant had said from the start. A door that never moved somehow ended up holding twice the odds of the one you originally, confidently, chose. Gather just 23 people in a single room, a group smaller than most classrooms, and the odds that at least 2 of them share the exact same birthday, month and day already exceed 50%. Push the group to 70 people, and the odds climb past 99%, practically a certainty, despite there being 365 possible birthdays to go around. The result strikes most people as impossible at first, since intuition tends to compare one person's own birthday against everyone else's in the room, a comparison that would indeed require dozens of people before a match became likely. But the actual calculation is not about your birthday matching someone else's. It is about any 2 people in the entire room matching each other, and the number of possible pairs in a group grows far faster than the group itself. 23 people contain 253 distinct possible pairs of people, each one an independent small chance of a shared birthday, and once you add up 253 small chances, the combined probability of at least one match climbs surprisingly quickly past the halfway point. The puzzle has become a standard teaching tool in introductory probability courses, precisely because the gap between the intuitive guess, usually somewhere near 180 people, and the real answer, 23, is so large and so reliably surprising to nearly everyone encountering it for the first time. The underlying mathematics traces back to a much older puzzle in combinatorics, studied by statisticians well before it ever became a favorite party trick used to win a friendly bet. A room feels nowhere near crowded enough for a coincidence like that, right up until the math quietly proves otherwise. 2 boxes sit on a table in front of you. One is transparent, and you can see it contains exactly $1,000. The other is opaque, and it contains either $1 million or nothing at all. Depending on a prediction already made about you before you ever entered the room, you may choose to take only the opaque box, or take both boxes together. Here is the catch. An entity with a remarkable track record of correctly predicting choices, correct nearly every time in the past, has already decided what to place in the opaque box, based entirely on its prediction of what you would choose. If it predicted you would take only the opaque box, it filled that box with $1 million. If it predicted you would take both boxes, it left the opaque box empty, reasoning that a greedy chooser deserves nothing extra. By the time you actually choose, the boxes are already filled or empty, fixed and unchangeable. The physicist William Newcomb devised this puzzle in the 1960s, and the philosopher Noah Zick published it in 1969, noting with some amusement that it reliably splits any room of thinkers into 2 camps that never fully persuade each other. One argument insists that since the boxes are already filled, your choice now cannot possibly change their contents, so you should obviously take both, and guarantee yourself the extra $1,000 regardless. The opposing argument insists that if the predictor really is as reliable as advertised, then choosing only the opaque box is simply what reliably wealthy people in this scenario do, and the numbers bear this out across repeated versions of the puzzle. Nozick reported that intelligent people, presented with identical information, walk away holding opposite convictions, and neither side has ever managed to fully talk the other one out of it. Two suspects are arrested together and immediately separated, each held in a different cell, with no way to communicate with the other. Each is offered an identical deal: betray your partner and stay silent yourself, and you go free while your partner serves a long sentence. If you both betray each other, you both serve a moderate sentence. If you both stay silent, the prosecutor can only prove a lesser charge, and you both serve a short sentence. Reasoned through purely as an individual, betrayal looks like the smarter move no matter what the other prisoner decides to do. If your partner stays silent, betraying gets you freedom instead of a short sentence. If your partner betrays you, betraying at least avoids the very worst outcome, a long sentence while the other walks free. Betrayal comes out ahead in both cases, and yet, when both prisoners follow that identical individually sound reasoning, they both end up betraying each other and serving the moderate sentence, a worse outcome for both of them than if they had simply managed to stay silent together. The mathematicians Meir Flood and Melvin Drescher formalized the scenario in 1950 while researching strategic behavior at the Rand Corporation, and the mathematician Albert Tucker later gave it the prison story that made it memorable and gave the puzzle its lasting name. The structure recurs constantly outside of any actual prison, in arms races between nations, in price wars between competing businesses, in overfishing by rival fleets, anywhere that individually rational choices, made without trust or coordination, quietly produce a worse result for everyone involved than cooperation would have. Two silent cells, two separate confessions, and a result that neither prisoner, reasoning correctly on his own, could have avoided alone. A village shares a single, open pasture where every herder is free to graze cattle without restriction. The pasture can comfortably support a certain number of grazing animals indefinitely, replenishing its grass a little each season. Each herder, considered individually, gains a clear personal benefit from adding just one more animal to the herd, since the cost of that animal's grazing is spread thinly across everyone who shares the pasture, while the profit from the animal belongs entirely to its owner. That same reasoning, however, applies equally to every herder sharing the pasture, and if each one adds just one more animal, and then another, following exactly the same individually sensible logic, the combined herd eventually outgrows what the pasture can sustain. The grass is grazed down faster than it can regrow, and the pasture that once supported everyone collapses, leaving every herder worse off than if all of them had shown restraint from the start. The ecologist Garrett Hardin popularized this scenario in an influential 1968 essay, using it to describe a broader pattern he believed showed up whenever a valuable resource is shared openly, and no single person bears the full cost of using more than their share. The pattern has since been applied well beyond literal pastures, to overfished oceans, to depleted groundwater, to congested roads, and most urgently, to a shared atmosphere absorbing the emissions of every nation and every individual at once, none of whom, acting alone, feels the full weight of the damage their own share contributes. Every herder did exactly what made sense for himself alone, and together, doing nothing wrong individually, they destroyed the one thing they all actually needed. A society commits itself to complete, unlimited tolerance, welcoming every viewpoint, every belief, every group, without exception or restriction of any kind. It sounds, on its face, like the most generous and open arrangement a society could possibly choose. But suppose one of the groups welcomed into that unlimited tolerance is itself fundamentally intolerant, openly committed to eliminating every other viewpoint the moment it gains enough power to do so. If the tolerant society continues extending its unlimited tolerance even to that group, refusing on principle to restrict it in any way, it has, in effect, handed the intolerant group exactly the freedom it needs to eventually destroy tolerance itself, along with every other group the intolerant one intends to suppress. The philosopher Karl Popper laid out this paradox in his 1945 book, The Open Society and Its Enemies, written in the shadow of the totalitarian movements that had recently devastated Europe, and he drew from it a conclusion that startled some readers expecting a simple defense of unlimited free expression. A genuinely tolerant society, Popper argued, must retain the right to be intolerant of at least one thing: active, organized intolerance aimed at destroying the tolerant society itself, or the society's own principle of openness, will eventually be used as the exact instrument of its destruction. Popper was careful to add that this exception should apply narrowly to movements that reject rational argument and openly advocate suppression or violence, rather than to any belief a majority simply finds disagreeable or offensive. A tolerance broad enough to protect its own destroyers, Popper concluded, was never really tolerance at all, just an unusually patient form of surrender. A judge tells a condemned prisoner that he will be hanged at noon on one weekday during the following week, but adds one further condition, that the execution will come as a complete surprise to him, meaning he will not be able to know in advance, on the morning of the hanging, that it is the day. The prisoner, left alone to think it through, reasons his way to what feels like an airtight escape. It cannot be Friday, the last possible day, because if he were still alive on Thursday night, he would know with certainty that Friday must be the day, since no days would remain after it, and a hanging he can predict with certainty on Thursday night cannot possibly come as a surprise on Friday morning. Having eliminated Friday, he reasons that Thursday cannot be the day either, for the identical reason, since Friday is already ruled out, meaning Thursday would become the last remaining possibility, knowable in advance the moment Wednesday night arrives. The same logic eliminates Wednesday, then Tuesday, then Monday, until the prisoner concludes with apparent certainty that no surprise hanging is possible at all under the judge's stated conditions. Confident in his proof, he stops worrying entirely. Then, on an entirely ordinary Wednesday, the executioner arrives at noon exactly as promised, and the prisoner is genuinely, completely surprised, precisely as the judge's original condition required. Logicians have debated for decades exactly where the prisoner's seemingly flawless chain of reasoning goes wrong, since each individual step in it looks sound, and yet the conclusion it reaches is directly contradicted by what actually happens. The argument that proved the hanging impossible turned out to be no obstacle at all to the hanging itself. You agree to take part in an unusual experiment. On Sunday you are put to sleep, and a fair coin is flipped, though you will never see the result. If the coin lands heads, you are woken once on Monday, briefly interviewed, and the experiment ends there. If the coin lands tails, you are woken on Monday, interviewed, put back to sleep with your memory of that waking wiped clean, and then woken again on Tuesday and interviewed a second time, with no way to tell whether any particular waking is the first or the second. Each time you wake during the experiment, you are asked a single question: how confident are you that the coin landed heads? The philosopher Arnold Zuboff first raised puzzles of this general shape, and the philosopher Elgar sharpened this exact version in 2000, and the puzzle has split thinkers into two camps ever since. One camp answers one half, reasoning that it was, and remains, a perfectly fair coin, and nothing you experience upon waking gives you any actual new information about how it landed. The other camp answers one third, reasoning that across many repetitions of the experiment, twice as many total wakings follow a tails result as follow a heads result, so if you consider yourself a randomly selected waking moment rather than a randomly selected coin flip, the tails outcome should feel roughly twice as likely from the inside. Both camps can defend their position with careful, consistent mathematics, and the actual disagreement traces back to something deeper, a genuine ambiguity in how probability applies to your own uncertain position within an experiment that has already happened around you, rather than to you making a fresh, ordinary prediction about the future. Waking up in that room, you would know exactly how confident to feel, and philosophers still cannot fully agree on what that number should be. Roughly 100 billion humans have been born throughout the entire history of our species, and you happen to be somewhere near the end of that count, one particular person among all of them, born at your own particular point in the sequence. The doomsday argument asks you to take that fact seriously as a piece of statistical evidence, rather than dismissing it as a coincidence with nothing to teach you. If humanity were destined to continue for millions more years, populated by trillions upon trillions of future people, then any individual human, selected at random from the entire eventual population, would almost certainly find themselves born extremely early in that vast total count, among the first sliver of a percent. You, however, find yourself among roughly the first 100 billion, a comparatively tiny slice of any astronomically large future population. The physicist Brandon Carter first proposed reasoning along these lines, and the philosopher John Leslie developed the argument further, suggesting that your own relatively early position is itself mild statistical evidence against humanity having an enormously long future ahead of it, evidence that should modestly shift your expectations toward a nearer, rather than a more distant, end for the species. The argument has drawn sharp and sustained criticism. Many statisticians argue that treating your own birth as if it were a random draw from a probability distribution smuggles in an assumption that does not hold, since you did not actually choose your position in history from some pool of possible people the way a ball is drawn from an urn. No fully satisfying rebuttal has emerged either, which is part of why the argument has stayed alive in philosophical debate for decades rather than being cleanly dismissed. Nobody chose their place in that count, and the argument over what that placement is allowed to tell you has outlived every attempt to settle it for good. Picture a sealed box divided into two connected chambers by a wall with a single tiny door, and inside the box, gas molecules moving at a wide range of different speeds, mixed thoroughly throughout both chambers. Now imagine a tiny imaginary being stationed at the door, fast enough to observe each molecule approaching and to open or close the door selectively, letting only fast-moving molecules pass into one chamber and only slow-moving molecules pass into the other. Given enough time, the being sorts the gas completely, one chamber growing hot with fast molecules, the other growing cold with slow ones. And this sorting appears to happen without the being spending any energy at all beyond opening and closing a door, assumed to be effectively frictionless. That result should be impossible. The second law of thermodynamics states that the overall disorder of an isolated system can only increase or stay the same over time, never spontaneously decrease, and yet the demon sorting looks like exactly the kind of spontaneous decrease in disorder the law forbids, a hot side and a cold side emerging from a uniformly mixed gas with no external energy input. The physicist James Clerk Maxwell proposed this being, later nicknamed Maxwell's demon, in 1867, specifically to probe whether the second law was a strict universal rule or merely a statistical tendency that a sufficiently clever, sufficiently small observer might quietly circumvent. It took physicists nearly a century to close the loophole convincingly, eventually showing that the demon's own act of observing and remembering which molecules to let through requires erasing information at some point, and that act of erasure itself generates exactly enough additional disorder elsewhere to keep the second law fully intact after all. The demon never actually got away with anything. It just moved the bill, somewhere physicists took 100 years to think to look. Suppose an intellect existed vast enough to take in, all at once, the precise position and the precise momentum of every single particle that makes up the universe, down to the smallest atom, at one exact instant in time. Given the laws of physics, which at the time were understood to operate with strict mechanical determinism, such an intellect could, in principle, calculate every future state of the universe with perfect certainty and every past state as well, with nothing left open to chance anywhere in the entire unfolding of reality. The mathematician and astronomer Pierre C. Mohon Laplace described this vast hypothetical intellect in 1814 in a work exploring the philosophical foundations of probability, presenting it as the logical conclusion of a universe governed entirely by deterministic physical laws, laws that leave no genuine room for randomness, only for our own human ignorance of all the relevant details. For Laplace, probability itself was less a fact about the world and more a measure of human ignorance, a tool for reasoning sensibly in the absence of the demon's complete information, rather than evidence that the universe contained any true uncertainty of its own. The rise of quantum mechanics in the early 20th century complicated this picture considerably, introducing genuine randomness at the smallest observable scales that appears to hold regardless of how much information any observer, however vast, might gather. Whether the universe is, at its deepest foundations, truly deterministic or genuinely probabilistic remains an open and actively debated question in physics today, and Laplace's original image of a demon, holding the complete state of the universe in mind, still anchors nearly every modern discussion of determinism and free will. No intellect has ever come close to holding that complete a picture, and physics itself has never fully settled whether one, even in principle, ever could. A hotel exists with infinitely many rooms, numbered 1, 2, 3 and onward without end, and on a particular night every single room in the hotel is occupied, one guest to a room, with no vacancies remaining anywhere. A weary traveller arrives at the front desk and asks for a room. In an ordinary finite hotel, a fully booked night would mean a flat refusal. In this hotel, the manager simply asks every current guest to move, all at once, from whatever room they are in to the room with the next number up, room 1 to room 2, room 2 to room 3, and so on for every single guest in the hotel. Since the hotel has infinitely many rooms, every guest has a next room waiting for them, and once everyone has moved, room number 1 stands empty, ready for the new arrival, even though the hotel was completely full only a moment before. The mathematician David Hilbert introduced this vivid scenario in a lecture during the 1920s to illustrate genuinely strange properties of infinite collections that have no counterpart at all in ordinary, finite arithmetic. The trick scales further than a single new guest. If an entire infinite bus of new travelers arrives at once, the manager can still accommodate every of them simply by asking each current guest to move to the room number exactly double their current one, which instantly frees every odd-numbered room in the hotel, infinitely many of them, for the infinitely many new arrivals stepping off the bus. A completely full hotel, and somehow, always, room for one. Seat a monkey in front of a typewriter and let it strike keys entirely at random, key after key, for as long as it lives, and then imagine that same process continuing uninterrupted forever. Given truly infinite time, the theorem states that monkey will almost certainly at some point produce the complete text of a Shakespeare play, every letter, every line, every stage direction, typed out in flawless sequence purely by chance. The claim sounds absurd on its face, given how astronomically unlikely any single specific sequence of characters is to emerge from pure random keystrokes, and the individual odds truly are almost incomprehensibly small, far smaller than any number that shows up in ordinary experience. But the theorem's actual content is not about how likely any one attempt is to succeed. It is about what happens to a probability, however tiny, once you allow it an infinite number of independent attempts to occur. As long as the chance of success on any single attempt is not exactly zero, no matter how small a positive number it actually is, repeating that attempt infinitely many times drives the overall probability of eventual success arbitrarily close to complete certainty. The formal mathematics behind this idea took shape in the early 20th century, developed by mathematicians studying probability and infinite sequences, well beyond the vivid image of the monkey that would later make the idea famous to a much wider audience. The monkey itself was never really the point. The theorem is a demonstration of just how strange and counterintuitive the concept of infinity becomes once it is allowed to actually operate on something as small and as ordinary as a single random keystroke. Given enough time, the theorem promises even the most implausible outcome imaginable eventually stops being a matter of chance at all. A person stands inside a sealed elevator, with no windows, no way to see outside, floating somewhere in the emptiness of deep space, far from any planet or star. If a rope attached to the elevator's roof suddenly begins pulling it upward with a steady, constant acceleration, the person inside would feel their feet pressed firmly against the floor, exactly the sensation of ordinary weight. Now picture that same sealed elevator instead, sitting motionless on the surface of a planet, held in place by ordinary gravity. The person inside would feel exactly the same downward pressure against their feet. Albert Einstein proposed this comparison in 1907 and later described the insight behind it as the happiest thought of his life, precisely because he recognized that no experiment performed entirely inside the sealed elevator, none whatsoever, could ever distinguish between the two situations, steady acceleration through empty space, or ordinary gravity holding the elevator in place on a planet's surface. The two scenarios are not merely similar. Einstein argued they are, at the deepest physical level, genuinely identical, a single idea that came to be known as the equivalence principle. That single insight became one of the central foundation stones supporting Einstein's later general theory of relativity, the theory that ultimately reimagined gravity itself not as an ordinary force pulling objects together, but as the curving of space and time around any object that carries mass, a curvature so subtle that its full mathematical description would take Einstein nearly another decade of work to complete, after this one deceptively simple elevator first suggested it to him. A single sealed box, and inside it no possible experiment that could ever tell the difference between falling and standing still. Two identical twins stand on a launch pad together. One boards a spacecraft capable of traveling at a significant fraction of the speed of light, journeys out toward a distant star, and returns home after what the ship's own clocks record as several years of travel. The other twin stays behind on Earth the entire time. When the traveling twin finally steps off the ship, the twin who stayed behind has aged considerably more, sometimes by decades, depending on how close to light speed the journey came. The effect, called time dilation, follows directly from Einstein's special theory of relativity, published in 1905, which showed that time itself passes at different rates for observers, moving at different speeds relative to one another. At everyday speeds, the difference is far too small to notice, but as speed approaches the speed of light, the effect grows dramatically, and a clock moving at extreme velocity genuinely ticks more slowly, from the perspective of someone who stayed still, than a clock that never left. What made the scenario feel like a genuine paradox for years was a natural but mistaken symmetry, the assumption that since motion is always relative, the traveling twin could just as easily be considered the one standing still, while the earthbound twin does the moving, which would suggest each twin should see the other as the younger one, an obvious contradiction. The physicist Pawl Langevin clarified the resolution in 1911, pointing out that only the traveling twin actually changes velocity, accelerating away and then decelerating to turn around and come back, breaking the symmetry between the two perspectives in a way that is not relative at all. Modern experiments using precise atomic clocks flown on commercial airplanes and orbiting satellites have confirmed the effect directly, in numbers that match Einstein's predictions with remarkable precision. One twin came home younger than the one who never left, and the clocks in orbit above you right now are quietly living out a small version of the exact same effect. Suppose that civilizations, once sufficiently advanced, eventually gain the computing power needed to run enormously detailed simulations of entire populations of conscious minds, complete simulated worlds populated by simulated ancestors who believe themselves to be living ordinary biological lives, unaware that they exist inside a computation at all. If even a single such civilization ever actually chose to run many such simulations, the total number of simulated minds produced would vastly outnumber the one original set of biological minds that ever existed in the real unsimulated universe. From that starting observation, the philosopher Nick Bostrom formalized an argument in a 2003 paper structured not as a single claim but as a trilemma, three possibilities of which, he argued, at least one must be true. The first possibility is that almost every civilization capable of eventually running such simulations goes extinct before actually reaching that point, whether through war, disaster, or some other collapse. The second possibility is that civilizations do survive to that point, but choose almost universally not to run such simulations for reasons of ethics, disinterest, or unforeseen constraints. The third possibility is that if neither of the first two holds, if civilizations do survive and do choose to simulate their ancestors in large numbers, then simulated minds would vastly outnumber non-simulated ones, which means any given observer, including you, reading this sentence right now, would be statistically far more likely to be one of the many simulated minds than one of the comparatively rare original biological ones. Bostrom has been careful to note that the argument does not claim we are definitely inside a simulation. It only claims that at least one of the three uncomfortable branches has to be the actual state of affairs, and each branch, taken seriously, unsettles a slightly different and equally fundamental assumption about what kind of a universe you are standing in right now. 50 rooms built from careful words, and the last one simply turns the question back around and quietly asks it about the room you are sitting in right now. That is 50 rooms now visited, 50 small traps built out of nothing but careful words, and if any one of them is still turning over in the back of your mind, that is exactly what a thought experiment is built to do. It does not need a laboratory to keep working on you, it only needs the quiet after the room is empty. The philosophers and physicists who built these scenarios were rarely trying to win an argument outright. Zeno was not trying to prove no one could walk across a room, and Schrödinger was not trying to convince anyone a cat could truly be both alive and dead. They were trying to find the exact place where ordinary thinking starts to creak, so that everyone after them would have to look at it directly instead of walking past it. Some of Tonight's rooms have tidy answers waiting somewhere in the philosophy that followed them. Others, the vanishing donkey, the surprise that arrives anyway, the twin who comes home younger than the one who stayed, still do not fully, not in a way that everyone agrees on. That unfinished quality is not a flaw in the design. It is the reason a thought experiment from 25 centuries ago can still be argued over at a dinner table tonight, in almost the same words Plato's students once used. You carry all 50 of these rooms with you now, quietly available the next time a choice feels harder to justify than it should, or the ground beneath some certainty feels a little less solid than it did this morning. The rooms will be there. So will the questions they were built to ask. For now, the lights are going down on this one, and the rest is yours to sit with.